No, I think this is where we left off last class, right? We was talking about the difference between DC and AC. So direct current. So what is direct current? Well, that's the charge, that's the voltage, but what's direct current? Yeah, it flows in one direction from negative to positive, right? So here we have a source, and then we have a source conductor, and we have a return conductor. We don't have that on AC. Produced by DC generators, batteries, thermocouples, solar cells, piezoelectric devices, electronically with AC to DC converters, and then bioelectric. What was the example of bioelectric we used? Uh, yeah, we're bioelectric devices. Major advantage is that DC can be easily electronically controlled. So every electronic device that I know of operates off of DC. Now we might plug it into the wall, but what we have is we have one of these guys somewhere. It's either built internal to the device or it's built external. Of course, your cell phone charger, your cell phone charger is obvious. You use the little bricks, right? Or you plug them into your computer, which provides a 5-volt power supply. So USB, two of the wires on the USB connector is for 5 volts, and that runs off there. Of course, my computer, it's real easy to see, right? There's a power supply right there. Of course, as oscilloscope, you see it's got a plug. It plugs into AC, but you don't see the power supply because it's what? It's built into it. This is a programmable controller. It plugs into Alabama Power or TVA, and you don't see a power supply because it's what? It's internal. So a lot of your power supplies are internal. And of course, these are power supplies. And when you play around with the trainers in here that we have, the black suitcase things, those have built-in power supplies. In fact, they have several built-in power supplies. They have two variable power supplies, a positive and a negative. They have a 5-volt fixed supply. They have a 12-volt plus and minus, no, 5 volts plus and minus 12. I can't remember if it's got a minus 5 or not. I didn't even know that. Should know that. We can electronically control it. So all PLCs, no matter what they do inside, they run off of DC. So this one over here, we call this a modular PLC. This one requires a power supply. So this is the power supply right here. Okay. What's the power supply do? It converts what? AC to DC. So electronic circuits that we're going to be doing. So these are some of the devices. We have voltage cells. Most people call them batteries. It's incorrect, but that's the commercial name for them now because everybody don't know that a battery means more than one, right? You understand? So a car battery is a true battery. All these A cell, all these AA, AAA, those were all technically cells, but everybody calls them what? Batteries. Now a 9-volt is a battery. If you ever tore a 9-volt apart, you'd see 6 cells in there, 1.5 volts per cell, 9 volts. Thermocouples, these take heat and convert it into electricity. Piezoelectric, these are these devices you can pop real fast and it generates an arc. So we can buy these cigarette lighters and stuff that does that, or light candles. Solar cells or photovoltaic cells, everybody knows these things. These things take light energy and converts them into DC. DC generators, these do it, convert magnetics by swinging a conductor to a magnetic field. Of course, batteries do it chemically, and then but all batteries do it chemically. They create a difference in potential. AC alternating current constantly swaps directions. The voltage source and an AC circuit constantly swaps directions with that, which causes, of course, the current to change, right? So AC, we have no source conductor and we have no return conductor because they're constantly doing what? Yeah, they're constantly swapping. So anybody that says you need to put your black lead on the ground in AC, they don't know what they're talking about. AC don't make any difference because it has no polarity, right? Your meter will measure exactly the same wherever you put your black and red lead. Less expensive to generate, extremely efficient to transmit power over distance because of what we're going to talk about. Voltage levels can easily be changed by transformers. AC motors are less expensive per horsepower. So there's several advantages to this over DC. But the problem is we have a problem doing what? Electronically control it. So what we mean by this is that what we're trying to do, what kind of bill do we pay every month? Power bill. So Alabama Power or TVA, we're actually on TVA here. TVA is actually up in the Tennessee Valley. So they get power, Bessemer gets their power from Tennessee Valley. And yet we still have the right voltages as everything here. But you remember, they're not trying to send current. They're not trying to send voltage. They're trying to send you what? Power. Now, the problem is that everything has resistance. So we have a conductor. And what determines the resistance of a conductor? Somebody in my class should know that, but this is a very important thing. What determines the resistance of a conductor? Yeah, the material it's made from. Yeah, the size. That's good. Size. Length, how far it goes. And what's the fourth thing? Conductors don't have a tolerance. No, that's what we're determining. The temperature. Metals, when they get hot, their resistance goes up, and when they get, that's why superconductors, if you ever did any research of that, they put those in liquid hydrogen, because liquid hydrogen is extremely cold, so it makes the resistance of these superconductors go way down, right? You understand? But only people that can afford superconductors are the U.S. government. But these guys still have resistance. It's just that their resistance is so low, right? You understand that? So the problem we have is Alabama Power is trying to get power to you, and power is equal to V times I. But the problem is voltage drop is equal to I times R. So if a wire has resistance, when we put current flow through it, it does what? It drops the voltage. Alabama, we don't usually worry about that because our conductors are so small, right? You understand? So short, excuse me. And we usually use copper or some type of alloy. A lot of times they'll coat the copper with a tin because copper oxide is an insulator. Copper rust is an insulator. So a lot of times you'll strip one and it'll look silver, but it's an alloy that has copper and other metals in it to prevent them from tarnishing real fast, right? So they're trying to send you power. So the main thing, if I transpose this formula here, I is equal to P over V. So that means the higher I can make that voltage, the less what? Current's required to send that power. So the lines running from Tennessee, these I think are 750,000 volt lines. So I mean, a TVA can send us 750,000 watts of power with 1 amp of current. But what's the problem with high voltages? Very dangerous, right? So and they're also all looking for earth ground because power is generated relative to earth ground. So this is why these high voltage lines are one thing, they're way off all the ground, right? You understand? So we can't get to them. And also they usually runs in groups of 3 conductors because one conductor would be really, really big and it would be hard to pull and hard to run. But when it starts getting closer to me and it starts getting closer to earth ground, what do they start doing? Stepping the voltage down. Of course, the current goes up, right, to deliver that power, and then they keep stepping it down till it gets to my house. And then we have a transformer right out there on our pole out close to our house. If you're lucky, it's got a big box out there somewhere, usually on the corner, where they have these transformers in it, which usually serves about 3 or 4 houses in a block. And what's the 2 voltages we use in our house primarily? Yeah, 240 and 120. That's what we call it, plus minus 10%. They try to get it to you as best they can. So their substations try to regulate the voltage for you, and then normally up on your transformers, they got, I think, three taps they can put on that transformer to get you as close to 120 and 240 that they can. So let's say the big advantage of AC is extremely efficient to transmit power over distance. Now, there's a lot of problems with AC that we don't have with DC, but we're not going to talk about those here. You'll learn about them if you take AC. And we'll talk a little bit about them if you take the motor control circuit, because you need to understand phase shifts and power factors and that kind of stuff. Are we okay? So this is why everything, most and a lot of times the PLC, of course, might allow you to control a little bit AC, but we're not going to do it. I'm gonna stop it there. So AC generators, we can do it electronically, or we can do it with bioelectrics, right? So automobile alternators, which used to be generators, but when the automobiles first came out, they used DC generators, and the DC by default, generators try to generate AC. I think y'all have all seen the magnet thing over here. Yes, no. Well, we'll do it. Let me pause this. Power plants have some really neat ones. What was neat is an electrical eel. Electrical eel puts out both DC and AC. It can put out 10 volts AC at 60 hertz to stun its prey, and then if it wants to kill it, it pops it with about 250 volts DC, which it'll shock you guys. I've seen videos of people trying to suckers zap them, and so they handle them with these big old insulated gloves. Huh? 870 volts you can. It would be hard for them to kill you because it's just like it's a lot like static electricity, so it discharges real fast. So they can't put out a constant 870 volts. So it's basically they charge up like static electricity, and then they discharge into these devices. But it can definitely kill like little fish and stuff like that, which is what they eat. But it will get you, just like static electricity get you sometimes, right? DC is more dangerous than AC as far as holding you because the current never changes direction. AC is a little more dangerous than that because another problem with AC is that if it passes through your heart, your heart pulses is controlled by electricity. If you get into 60 cycles per second and your heart tries to beat it, well, 60 cycles per second when it's used to beating at like 60 times per minute. So what can happen is your heart can go into what we call fibrillation, which means your valves and your heartbeat are out of sync, which means your valves are opening when they're supposed to be closing. So what happens is you can't generate any blood pressure anymore unless they do all, unless they get that defibrillator and pop you and try to get your valves and your heart back in sync with each other. So the DC will burn you a lot faster than AC will. So they're both dangerous, guys. But if you look at the lethal levels of current, they usually give you one for DC and one for AC. And believe it or not, women have a ratio than me. So we got a chart somewhere I'll show you. But you got to understand, you're around something that's that's safe if you stay safe, right? Y'all understand that? And this like what my other class is, it's more dangerous that you getting out here in your car and driving home than to deal with electricity as long as you do what you just follow safety rules. So you need to pay attention where you're at, just like when you drive. If you're up here texting on your phone, and trying to drive, you're gonna have a wreck, right? So most AC waveforms is referred to as a sine wave because it varies with the trigonometric sine of the voltage. That's just nice to know, and AC you'll learn more about that. But when we start dealing with AC, guys, you're going to have to start dealing with, if you want to really learn AC, you're going to start dealing with a basic trig. It's called right angle trig. Not, of course, trigonometry is the study of triangles, right? But we have all these different types of triangles. But what we deal with at AC is just right triangles. You understand right triangles? For that one angle is at 90 degrees, right? So this is basically the way AC is generated. This is called a sine wave. And of course, this is showing you, and it's generated on a circle. So we say one repetition is 360 degrees, but it's we try to specify electrical degrees. And if we come up here and stop this anywhere, so this right here represents the peak value. You notice anytime it's right here, oops, didn't want to do that. Anytime it's right here, that's at peak, right? You understand that? So if I stop it anywhere, if I can stop it here, it might not be the right slide. Oops, okay. If I can stop it, it would always form a right triangle. Dang it, won't let me do this. I need my other slide. So this is some terminology. So one repetition is called a watt cycle. Are we okay? By the way, this is out of my book. Then a cycle is one repetition of a waveform, or 360 electrical degrees. Frequency is the rate of the cycle measured in cycles per second, or hertz. So Alabama Power, or in TV, the power grid in the United States is 60 hertz. So that means these guys one complete cycle in 60 hertz. So that means one cycle only lasts 16.6666 milliseconds. And it's swapping polarity every 8.333 milliseconds. Milliseconds, guys. So for all practical purposes, this guy has no watt. Has no polarity. So this is why I didn't make any difference which direction you hook your meter up. Okay? So we have a lot of devices that work off AC. And then our PLC works off of DC. So we got to figure out some way that the PLC can control AC with what? With DC. And we'll look at some of the things that's available to us. Any questions? So some of our PLCs, like this one on the desk, this allows us to control loads with AC. So loads we hook up to either the AC load or DC load. Right now it's wired up, so it's running controlling AC load. But the input over here, or input into the PLC is DC. So we'll talk about different ways. So a PLC is a powers it up. So we say this is AC, and then what we put on when we bring information into it, what power we have. Right now we call this an DC relay. Of course, we all know relays, right? We talked to them about relays. So this guy here actually outputs to a relay contact. So what does that mean? We can actually set it up to control DC or AC in different voltages. So we'll talk about the different ways what we can actually control. This guy right here is DC, and then the input, so we bring information into it is DC, and the information we get out of it is DC. We'll talk a little bit about the next lecture about the basics of a computer. We need to understand a pretty good deal about computers because the PLC is a computer. And when you talk to people that know these, they're going to talk a lot of language that deals strictly with computers. So we'll look at that. And we're going to understand the binary number system, guys. So you won't be using it this semester, but anytime you deal with computers, you got to understand they only deal with ones and zeros, truths and false. So any questions on this? This is about all we're going to talk about here. And this will help us explain, what they do. We know we know the actual PLC itself, the internal circuit going to operate a fault. DC, it's electronic. But that don't mean that's what we got to control, right? You understand that? I'm going to knock that thing over. So chapter 1. Anybody got your book? If not, the PowerPoint should be okay.